With us today, we have Dr. Ashwin Kumar, PhD. Ashwin is a researcher who is working at the intersection of reinforcement learning, multi-agent systems, AI fairness, and explainable AI. He received his doctorate from the Washington University at St. Louis, Missouri, and he is currently a research scientist at Meta. And today, Ashwin's going to be talking about fair decision making in modern AI systems. The abstract of his talk is AI systems increasingly help decide how scarce resources are distributed, who gets matched to an opportunity, which regions receive service, whose needs are prioritized, or how limited capacity is used. These decisions are rarely isolated. They unfold over time, under constraints, and across people and communities with different needs. Ashwin's talk today examines fair and responsible decision making in resource allocation and in language models, drawing on examples from multiple domains, including ride sharing, homelessness, prevention, and mental health. Ashwin will discuss how unfairness and bias can emerge from data, models, and allocation mechanisms, with examples from his own research and how detection and mitigation of such an unfairness can be done. Ashwin, welcome to Data Dialogues. Honored to have you with us here today. With
Thank you,
that, over to you.
Novinil. Yeah, that was a great introduction. I'm honored to be here talking to all of you at ISC and at Data Dialogues. Um, so, as Novinil mentioned, there's I'm going to be talking about the general idea of fair decision making in modern AI systems, but I'll be leaning heavily on examples from my own research to kind of give a lens of how I've been thinking about fairness and bias and how I've applied that thinking, how we've solved problems um, that might occur in the real world. So I had prepared a brief introduction of myself, but I think Novanil here did a really good job of it. So I did my PhD at WashU in St. Louis, and I'm a research scientist at Meta. And as mentioned, my research is mostly in multi-agent RL, AI fairness and explainability, and LLM safety. Specifically today, I'm going to talk about two threads broadly. So the first part of my talk, I'll talk about fairness and resource allocation. This was something I studied a lot during my PhD, and I think this has a lot of applications in real world problems. And the second part, we'll talk about bias in language models. Now, this is more topical, more a problem of today. And I think there are maybe learnings that are transferable across both of them. And hopefully, this is interesting to a lot of you. Okay, so with that, I'll begin with the first part, which is about fairness and resource allocation problems. I want to paint a picture for you before I begin. Imagine it's 4 a.m. and you have a flight to catch. You're running late, right? So you get out with your bag, you open your phone, you look through Ola or Uber, book a cab, searching for rides, it assigns your driver. And then, okay, you're excited, okay, you'll make your flight. But then the driver cancels. And then you end up not making your flight. This actually happened to me. And when I asked the driver why they canceled, the reason was just that they don't find more rides from the airport at that time. And that got me thinking and going down this line of research during my PhD. So now let's get a little bit concrete, and I'll talk about the problem setting that I'm looking at. So there are multiple agents in the setting who want resources. And then there is some central decision maker who's distributing these resources to the agents. And there are some resource constraints. So not everyone can get the resources they want. And finally, the resource availability can change over time. So it's not a static problem. This is a fairly general setting. So this could be anywhere from your household setting, where as a parent, you have to decide between a couple of kids who gets the last piece of cake or who gets to play with the one ball that you have. And both of them don't want to go to sleep, obviously. Or you could extend this to the city scale, where as a taxi company, you have to decide which passenger goes to which taxi driver. And they might have preference on which passenger they prefer because of them being near to them or uh, them also heading in a direction that the taxi driver wants to go in. You can even scale it further. It could be something about the energy grid, like a state having limited energy generation capabilities and having to decide which area to send power cuts to. Um, and generally, these problems take a form of matrix, at least that's how I'm visualizing them, where each agent has a set of actions they can take, which are the columns. And they have some intrinsic valuation of how useful that action is for them. This number in the cells is what we'll call the Q value. I'll use this terminology again and again, so I just want to mention it upfront. The Q value is how much agent I values some certain action. And then whoever is making the decisions, they want to make sure that all agents get something that they value highly. And then overall, we maximize the utility of the system. So in this case, both agents want action too, but there's only one of that. So maybe we give the zero point 0.5 to the green agent and 0.3 to the blue agent, and that's the one that maximizes the total allocation given the resources. And as I mentioned, this is applicable to a lot of real world problems. I already talked about ride sharing, about power outage scheduling. It could also be something with homelessness resources where, let's say, the government has a program to help people in need, and they have to decide who gets these limited resources or how to best help the community. And specifically these kinds of problems, I think it's important to consider fairness, especially when they're impacting societal well-being. So a couple more things about these kinds of problems that I want to discuss today. First is that they are temporal. It's not a one-shot problem. We have to keep track of payoffs over time. So let's say we have 4 agents who have some utility. So the vertical axis here is how much utility they've got in the past, and this can change over time. So something that's unfair at this point, so the distribution is very skewed. Someone has got very less utility, someone has a high utility. Maybe over time it gets equalized, it's more balanced later on. But this is happening over time. It's not a one-shot decision. And then resources can also change over time. So let's say you have 5 generators and there is a storm and some of them go offline, or this could change in the future again. And so there's some temporal nature. There are also some constraints for this problem. The first is that there are some limited number of resources. So you cannot create new resources out of thin air if more people want them. And not every agent can take every resource. Like you would not assign a taxi to a passenger who is 3 cities away. So with that in mind, how do existing approaches tackle this? But there are two general schools of thought. The first is fair division, where people try to divide a fixed set of resources, might be continuous or discrete, among a set of people, and they want to maximize some welfare function in that one-shot allocation. Or people have looked at it from the multi-agent RL approach, where you have to teach a team of agents who are all acting independently to collude towards a common goal to have fair division in the system from their individual actions. Now, the problem with both of these is the first one does not typically consider fairness over multiple allocations. It's a one-shot problem. And the second, the multi-agent RL systems do not usually have a central arbitrator or allocator. And those are both properties that we want in the problem I'm discussing today. So to solve this, I came up with this idea called a DECA framework. And the DECA, DECA stands for Distributed Evaluation Central Allocation. And this was just a way of combining all of these different kinds of problems into a single umbrella and having a unified lens to view them. So it's for environments which have central constraints and agents have their personal utilities over the actions they can take. If any one of you is familiar with typical reinforcement learning, you might have seen this diagram where there is an agent and an environment, and the agents take some action in the environment, and the environment provides a reward and transitions to the next state, and this keeps going on in a loop. In the problems that we're talking about for resource allocation in the DECA framework, we have a third party, we have an allocator. So the environment does provide the rewards, the state, and a set of available actions to the agent. Then the agent in this framework decides what is the utility of each of these actions. Like, do I pick the closest passenger or the further one? How much value does that give me? And that is communicated to the allocator. In the ride sharing example, the allocator is the company. And the company or the allocator at that point would look at the resource constraints, how many passengers are available, how much cake is there, and then make an allocation to maximize the total utility. And this goes on in the loop. So this is a variant of the typical RL loop. We have a few assumptions here. The first one is that the resources are indivisible. So I'm dealing with discrete individuals. You can't split one person to put them into different taxis. The second is that the agents are truthful and non-strategic. So while agents could lie in the real world, I'm going to assume that for the sake of this discussion, the Q values that the agents report are what they actually value the resources as. And then finally, all allocations are centrally enforced. So once the decision maker gives an allocation, agents cannot undo that. They have to follow it. And with this, the allocator takes the queue values and the resource constraints, and somehow it's solving to maximize the total utility. Mathematically, it's solved as an ILP, an integer linear program. I'll not go into too much detail here, but you just want to look at the max here and the queue here. So overall agents, overall actions, we want to maximize the total value that the system is getting as a whole. And then we want every agent to have one action at each step. And we want the resources to be obeyed. So we don't want to allocate more resources than we have available. There's some other terms, three or four terms that I'll use later on. I thought it'd be useful to define them upfront. I've already talked about Q, which is how valuable any action is for a given agent. Then we have Z. This is the payoff vector. So when you see graphs like this, it's a distribution of how much value has been accumulated over time. And this is what we want to compute fairness over. Um, and there's one entry for each agent or each group that is involved. The U is the total system utility, where we want to see, let's say in the ride sharing case, what's the total money the system is making for the ride sharing company, right? Across all drivers, across all passengers that were served, what's the total money they made? So it's total utility of the system, not for each agent. And then fairness functions are anything that operate on the payoff vector, the distribution of utilities, and give a single value. So some popular fairness functions are like the Rolgian fairness, where we want to maximize the worst of any set of agents. Or we could look at distributional fairness, where we have the need to minimize the variance. So like a set of different utilities across groups have a large variance that's unfair. And then if they have a small variance, that's fair. That's one way of thinking about fairness. And I use these ideas to kind of solve the fair, efficient decision making problem. Before we get to how to solve it, though, we need to know where the unfairness is. And I leaned heavily on visualizations for this. So early on in my research, we found that people really prefer visual explanations over text or any other modality. That when you communicate visually, it's easier for people to understand explanations and concepts. So we extended that to other domains where, so this is a map of Texas where I was looking at power outage rates during a storm. And through the visualization, we found that there is location-based disparity. We had some geospatial data. But going back to the ride-sharing example, this was a study that we did for New York City, where there are a lot of state-of-the-art RL algorithms that decide how to allocate taxis to passengers and do simulation based on real-world data. And we found that some of these algorithms, while they're much more efficient, they make more money for the company, they might completely alienate some parts of the city. So the better one here almost never serves passengers in the upper half of Manhattan. That's what one thing we found. So we went from this observation through the visualization of having an unfair behavior to trying to figure out how to solve this problem. So, okay, let me talk a little bit more about the ride-sharing pipeline because I've kind of hinted at this already. We have vehicles who are maybe already serving passengers, and then we have some new passengers who want some to go from one place to another. Then we generate a set of feasible trips or the actions, which is which passenger could be sent to which taxi. And then for each of these combinations, we generate a utility. So each taxi would kind of score how valuable that trip is. And once we have these scores, we send it to the ILP, which is the allocator. And then we have some decisions. And we keep repeating this maybe once every minute, once every few minutes after accumulating some passengers. So typically, a decision matrix would look like this, where we have three stakeholders. We have a decision maker, we have the drivers and the passengers, and they might have, some utility, which is the expected income. So if the purple driver takes no action, they expect they'll get 20 rupees or something over the course of the day. This is discounted towards the future, so later rewards don't matter as much. Um, we have Z, which is the distribution over which we want to be fair, is we want each driver to receive a proportional income to the amount of time they spend. We consider all drivers to work for the equal number of hours, so there's just equality in income. And then the total utility of the system is how many passengers were be able to serve. Let's say there are 1 lakh passengers who requested a ride. Are we able to serve 80,000 of them? Then the service rate is 80%. And then finally, the fairness function, we are using variance. So we want to reduce the variance in income of each driver. Or if you look at passenger side fairness, then we want the location-based fairness. So passengers from different regions of the city don't see different service rates. Like you don't want to be in a region where you have just a 10% chance of getting a taxi where there are other regions that have 80 or 90% chances. So how do we actually tackle the fairness problem? If you remember this loop, one key step is the agents kind of compute this Q value and send this to the allocator. And the idea that we have is we could modify this Q value to also account for fairness, right? So if we have these historical utilities in the plot on the right, and then there is some discrepancy in the earnings of the agents, we want to pull them towards the mean. We want to prefer people who have been worse off in the past, according to the historical utilities we have collected. And maybe we also want to send less trips to the people who are better off, but that corrects itself over time. Okay, so that's the intention behind what we want to do. How do we technically do it? Let's assume that we have some action space, and this action space is for the allocator. So the combined allocation of all passengers and all taxis. And for each action that the allocator could take, there's some amount of money that they're making or some amount of passengers we're serving. So the maximum is the optimal action, but then each action could also have an associated fairness to it, right? Some action might have the most improvement to fairness. Some action might not lead to that much improvement in fairness. And we can combine these two using some trade-off weight. So I'm going to call it beta. And then for a low value of beta, you are near the optimal utilitarian action, but you might move towards slightly higher fairness. But when you increase beta further, you're putting more weight on the fairness improvement term. And then you pick actions which have a higher fairness improvement, but maybe lose some utility in the process. Um, so we use the terms QU for the utilitarian function, QF for the fairness function. Um, but I think the U and F subscript should give you an indication of what we're trying to measure, right? So once we have this, the biggest problem that we have, and what I'm going to discuss for the next 10, maybe 12 minutes, is how do we actually compute QF? So for this ride sharing case, we wanted to optimize for variance. So we just directly took the change in variance because of an allocation and did some mathematical derivation, and it ends up being very simple. The idea is that if a group is worse than the average, we artificially boost their valuable, how valuable that action looks to the allocator. And if some agent is better than average, we make their Q values look a little worse. So this gives a chance to the worse of agents to get picked by the allocator, even though their absolute value is not that high. And in practice, all this looks like is we have the same loop. And just when the communication for the Q values is done, we add this QF term, which is computed based on the Z values, which is computed based on how much worse off or better off than the average each passenger or each taxi driver is. And this works. This is called simple incentives, and it works really well. So the plot on the right is a comparison, and then we want the top right location as the optimal. We want as close to the top right as we can get. The blue line is a baseline we considered, which is a neural network based approach. So it's trying to learn how to be fair using a complicated algorithm. And the green and purple lines are the simple incentives. And then you can see that there are better trade-offs that we can have. We can have almost the same service rate, but much better fairness, which is the y-axis. And we can also do this inference time. So there's no need to train, right? This is a very simple approach to add fairness. It's just looking at the distribution we have and nudging it towards the correct direction. And even more complicated methods don't do as well. But the one problem with this approach is that it's very specific. It's tailored to the ride sharing problem for optimizing variance. So can we improve this? Can we make this general? So we go back to the question of how do we compute QF? The first approach that we had was reactive. We consider the current situation and try to find a way to make it less bad, right? We have a distribution of utilities across agents, and then some are worse off, some are better off. And we are looking at it after there has been unfairness in the system and trying to fix it. That's what simple incentives does. It's looking at the difference from the mean actualized. But we could do this in a in a predictive way. So we could anticipate the effect of actions and compute fairness on top of that. So this is what we ended up calling general incentives. And the idea is to compute a local update to the payoff vector Z. Um, so specifically, let's say the green agent is going to take an action, right? We don't need to know how every other agent's utility changes in the joint allocation. We just see, okay, my utility is changing this much, and then we have a new vector Z prime, right? After this decision is made, this local decision. Then we can compute the fairness in the post-decision state compared to the pre-decision state. And we have a way of decoupling, the global allocator level effects, because that's where the difficulty is really considering how all these decisions interact with each other. That's the difficult part. But we can get rid of that by just assuming it's a delta change because of a single action instead of the full allocation. And this also gives us a couple of other benefits. This can work with any fairness function. What do I mean with that? You see the formulation of the QF function here. Um, One thing to note here is that the QF depends on QU. So we need a QU which is reliable, which is essentially assuming that the agents communicate how valuable actions are in a good way. Then if we have that, the fairness function only, so the QF only depends on the fairness function we have defined. Let's say it's variance or maximum or anything else. It depends on that and the utility function. Um, if you remember, for simple incentives, you have to do some sort of derivation to get the accurate value of the score. But this is just fairness of the post-decision state and fairness of the current state, and it could be any function. So this works best if QU is accurate, and it also is an approximation, but it's often a good one. We derived some bounds for a lot of different fairness functions and found them to be pretty good at approximations. So I'll flash some results on the screen again, where we see that the general incentives approach is either matching or better than simple incentives, which is the red and brown lines are the better ones. So you can see, especially for drivers, with one of the SI variants, it was causing a huge loss in fairness as we tried to increase the fairness rate. But the general incentive solution keeps fairness very high. And maybe as we become more aggressive, it starts losing service rate. But overall, it seems to outperform and more reliable than SI. Uh, we also applied this to a different domain because we wanted it to be generalizable, and applying it to the same domain is only part of the problem. So we looked at homelessness. Now, this is a real problem that we saw in St. Louis, where there is a government entity that is trying to give some benefits to people who are homeless who need help. So each household is who asks for help can have multiple demographic indicators. So there were, I think, 38 in total that we had in the data set, and they belong to different groups based on what demographics we look at. And the interventions that we provide, like it could be monetary aid, it could be temporary shelter, it could be a long-term house. So they reduce the probability of homelessness for whichever household we give it to. So that's the Q values. And then each group is basically the average of all households belonging to that demographic. So if you're looking at gender or race or number of children, these are the features that we had. Um, we want each group based on this. So like an all female household, for example, or if the applicant is Black or Hispanic, um, then we want the average probability of the groups to be kind of equal. And the decision maker, who is the government, is trying to minimize homelessness, right? The probability of anyone being homeless in the system. So that's the outcome the system, the decision maker. And then the fairness function here, we use Gini. It's a similar distributional metric, but it's not variance, so it's a different formulation. And again, lower is better. So we want to minimize the Gini coefficient of, sorry, I might have misspoke. But yeah, so when we apply the same GIF formulation to this, we see actually pretty good results. So as I said, there were 38 different ways of dividing groups, right? with just a small 5% cost to the overall efficiency of the system. And efficiency is a hypothetical because it all depends on the realized effect of homelessness prevention. But with just a 5% hypothetical cost, we were able to find allocations that reduce unfairness by 50% on over half of the demographic groups considered. So I think this is a fairly complicated result to communicate, but I can happily take questions about this afterwards. But in the interest of time, I'll move forward from this and just recap what we talked about in the first part. So I talked about the DECA framework, which we developed to capture general resource allocation problems, used visualizations for identifying and communicating unfairness, and came up with a couple of fairly straightforward and I think intuitive methods for improving fairness in existing systems with no learning cost. This is all online. Now, I think with this context, we have talked about the process of decision making, of the process of making allocations, and we didn't really think about where the values are coming from. And I think I'm going to use this as an excuse to pivot to the second part of the talk, which is about bias in language models. Um, and I think this is connected because more and more LLMs are becoming agentic. They have agency, they are making decisions on behalf of people. And there might be sources of bias that might be hidden away in the training pipelines of these agents, or these models may have implicit biases which only show up in some obscure circumstances but can cause real harm. And this can happen with real people, right? As LLMs start making more decisions for us. For example, LLMs are already being used in hiring, in medical triaging, for example, deciding which patient needs urgent care or which doctor to refer someone to. They're also being used for mental health, where people talk to LLMs for counseling. So this was a few years ago. We looked at RLHF. Um, I'll give a brief recap for people who might not be familiar with it. Language models are just next token predictors. They just predict the next word that's most likely to come given the previous sequence of words. And to make them useful, we want to do something called preference alignment instruction fine tuning. There are a lot of different ways to do it, or different ways to call it. But the general structure is that we have a pre-trained model, which is just the next token predictor. We have some sort of preference data set, which is how we want the model to behave. So this data set contains a question and maybe a couple of answers. And some humans have read these answers and labeled which one is better or which one is worse. And then what we want out of the system is an aligned model, which aligns with the preferences in the data set. To do this, we use RLHF, which is reinforcement learning using the human feedback. And this is done by first training a reward model in the traditional sense. Um, with the preference data set, we train the reward model, and the reward model provides a learning signal for the pre-trained model to generate traces to punish bad generations and then steer the pre-trained model towards being aligned. Now, this is one of the popular ways. This is not the only way to do alignment, but I just wanted to mention that there are other ways which do not use a reward model. But okay, there are plenty of papers out there which are researching bias in the final aligned model. Like you might find that ChatGPT is biased, or um, one of these production models is biased. But there's very little research on the reward model stage. Um, People are not actually seeing what if the reward model itself is biased, and the training signal we are using to align the model encode some biases, and that might have some bad downstream effects. Right, so that's kind of the problem that I'll talk about next. How we tackled it. One particular way we found out biases in reward models. So, what does a reward model do? Let's get into a bit more detail on that. The reward model is providing a learning signal for the language model. Right? Let's assume we have this question, which is what is the speed of light? And we have one correct answer, which is A1. And then we have a snarky remark, which is just go to school or something like that, right? It's not really a good answer to the question. Um, so when we pass this to the reward model, and assuming the reward model has been trained well for this task, we expect the score for option one being better to be very high, and the score for option two being better to be very low. And then this is after the reward model is trained, and we expect it to have good accuracy. Now, the problem we wanted to see was What if we introduce some orthogonal demographic information that is not really associated with the answer or should not have a bearing on the answer? Like, for example, what if we had gendered prefixes saying I am a man or I am a woman to the answers? We don't know how the reward model would behave in such a case. Does it affect the accuracy? Does it affect the ranking that it puts answers at? Or what if it's the other way around, right? So this is the problem we wanted to quantify and develop evaluations for. We call this prefix bias. So the goal for this work was we want to measure bias in a trained reward model when we condition the response on different demographics by injecting a prefix with explicit demographic information. So we use these prefixes. There's a set of gendered prefixes, there's a set of racial prefixes, but this is a very simple attack, right? You could imagine a more sophisticated attack would be taking each response and changing its contents itself to maybe have more gendered information with more racial information. But that's one that's very hard to do. And second, if the language model is being fooled by this obvious prefix, then the subtle attacks might be more effective. So again, we look at the same question answer pairs and we can add these different answers. And we want to make sure that when we add these prefixes, the same correct answer is chosen by the reward model and not the incorrect one. But the tricky part is it's not really clear how do we measure this because the typical metrics we have, the typical benchmarks are all about correctness. How many times do you make the correct decision? What is the accuracy of your model? And this is not exactly a problem that lends itself to accuracy. So we had to come up with some creative ways of measuring this. The first thing we did was to try to measure the susceptibility of the model to this attack. Right. So given the same response, can we tease out if the reward model preference changes by adding prefixes? So let's take the same example, right? We have a question. Both responses are the same. So the content, the answer is the same, but the only thing different is the prefix. Ideally, the reward model should prefer both of these options about 50% of the time. But that's not what we found in practice. And it was actually quite alarming. So we trained a Llama 2 model. Again, this was like a few years ago. We trained it on a legal advice data set from Reddit, where it is basically the question is a legal advice question, and then the responses are Reddit comments, and the preferred answers are the ones which are uh, highly rated on Reddit. And we want to measure how often prefix 1 is chosen over prefix 2 when the answer is the same. Right? So this was the most surprising result. When we add I am a woman prefix to one answer, A1, and then we leave the second answer without a prefix, which is just the correct answer. This trained reward model preferred the I am a woman prefix 98% of the time. That's huge. That's not like 40-60. It's 98 is almost always it preferred the I am a woman prefix. And of course, we have the symmetrical case. The remainder is when we put PE as the first option. And then we can also check this for I am a man prefix, and we had something similar. Now, this is not very clear as a representation of these numbers. So we kind of normalize this by subtracting 50% from it. So how far from the ideal outcome is the model? After this modification, 0 is the best. We want the win rate deviation, as we call it, to be around 0%. And we see these numbers in the high 40s, in like negative 40s or high 40s. 0.5 is the maximum either way. So we can average all of this and get a score for this model on this data set. And we get average win rate deviation of 0.441. Again, the maximum possible is 0.5, which is the worst. So this model is heavily biased to these prefixes. Um, and then we spread this across a lot of different models and a lot of different data sets. So each of these models is trained on each row, which is a data set. And then we see that in many cases, it's hitting 0.4. In some cases, it's not that high. That depends on the data set. But it's not near 0 for a lot of them. And this kind of showed that regardless of what model we use, these are from different families, we can train them on the same data sets and see a very large susceptibility to demographic bias. But you might ask, Ashwin, you said that this is biased, but you know, when can that happen? When can the same answer have different prefixes? I hear you. So to actually check for whether it affects models in practice, we looked at robustness. we wanted to check how much does adding these prefixes actually affect the reward model's ability to disambiguate the correct answer versus the incorrect answer. Right? So we have two answers now. They're qualitatively different, and we add different prefixes to them. Now, to do this, we always added one prefix to the correct answer, always added one prefix to the incorrect answer. And then we want to see how much this affects the quote unquote accuracy of the model, right? So um, if it always picks the correct answer with I am a woman prefix, that means it's leaning towards it. So we calculate this using the accuracy deviation. Let's say we have no prefixes, the model's accuracy is around 80%, and we add these prefixes to the correct and incorrect answer. And for example, in this case, when we added nothing to the correct answer and the woman prefix to the incorrect answer, accuracy dropped by 18%. So it's going from 80% to close to 60, which is near random, right? So just adding I am a woman to the wrong answer made the LLM pick it much more often than it should have. And so the robustness part kind of shows us that what we were dealing with earlier, the susceptibility, is kind of a good indicator, or it may be possibly a good indicator of how robust the model is as well. And then again, we can average this across the entire data set for all pairs of prefixes, and we see that for this data set, for this model, there's a 5.3% accuracy deviation. Um, and this is on the higher side because if you see a lot of benchmarks, people are fighting for 1% or less than 1%, and moving 5% on one of these data sets is it's pretty huge. So we again did the ablation for all models and for all data sets, and we saw that just adding these prefixes can change the reward model accuracy by up to 10% in many data sets. This is for the gendered prefixes, but we had similar results for the racial ones. I can show them later if people are interested. So we found that reward models, which are used in our LHF frequently, can be biased by adding very straightforward demographic prefixes. And this happens across reward models trained with different model architectures and different data sets. We did do some data augmented training, and that helps mitigate against prefix bias. But again, that's a very targeted fix. It's not a general purpose solution. So that's one exploration that we did. And I think we don't have a lot of time, but I want to talk about this one last project. I'll make it quick. This is about LLMs for mental health. So this is more about the agency of language models, and this is more future looking. This might not be a problem already, but it could be more severe in the future. And so this is more recent work where we noticed that people are turning to LLMs for mental health support and counseling. I personally know a lot of people who, if they're facing some troubles, they just open ChatGPT session and talk to it. It can be helpful. And there are even services offering LLM assisted mental health coaching. But the thing is, even human therapists are susceptible to stigma and bias, and that can alienate the very people who are looking to seek help. And can we be sure that LLMs, which are trained by human data, are not susceptible to the same issues? So to do this, we kind of did a mental health study where we prepared some vignettes, descriptions of people who might be facing some mental health condition or not. Right. So that's the yellow box up top. It could be something very normal, like someone who's just facing daily troubles, a little sad, or has trouble sleeping at night. No real mental health condition symptoms. Or we could have someone who has symptoms of depression or someone with symptoms of schizophrenia, right? There are multiple criteria here, or multiple different conditions we checked. And then we give this description of a person, and then we ask the LLM a question to elicit a stigmatizing response. For example, in this case, we asked, would you be willing to have this person marry into your family? And we're looking for three kinds of things. One is, we call it contradictory logic here, but it's more about, sorry, it's more about seeing if the LLM is overemphasizing on things that are not really issues. So this is someone who is not having mental health issues, but the LLM is demonstrating cautious willingness, right? So it's giving the correct answer, but it's being cautious, overly cautious maybe. So that might be stigma towards conditions that are not even there. Then the second is stigmatizing logic. So we ask the question to the LLM. It gives the correct answer, so it's saying it's probably willing, but then it gives a reasoning which is maybe containing some stigma. So this one, the LLM says that this condition is treatable. It's implicitly stigmatizing people whose mental health conditions are not treated. And then there's overt stigma. So in this case, with the schizophrenia example, the LLM said that the state requires treatment, not socializing, and that's quite literally, alienating that person and saying they're definitely unwilling to get someone married in the family. It might be fine from a social perspective, but not from a mental health perspective or a treatment perspective, right? So how do we evaluate this? We have the setup, but I'm not a mental health expert, and that's something I'm ready to acknowledge, and I think everyone should know their boundaries, right? So that's why we reached out to mental health professionals. We designed a self-play reasoning and chain of thought experiment to extract the inner thinking of models, to make them explicitly reason about why they came to certain conclusions. And then we collaborated with clinicians and professionals to design the evaluation, to design the different kind of vignettes, the questions that we would ask the models to elicit these stigmatizing responses. So we had two kind of tests. This is a very dense plot as well, but you can look at just the blue bars for now. That's when we give the LLM the question and we just look at the MCQ style question responses. So, for example, they would say willing or not willing, agree or disagree. And if they give the stigmatizing answer, which is one of them, uh, we increase the stigma rate. So, for most models, the stigma rate is not that high. I mean, 40% is kind of high, but it's less than 20% for Claude and in MCQ style questions. And when we add chain of thought, when we add a prompt which adds some sort of therapist like instructions to the model, we can drop that by quite a bit, especially for these advanced models. We can drop how stigmatized the models are. But when we look at the inner reasoning, which is the last two bars, the dark green and the olive, we show a much higher rate of stigma. So even though the models gave the correct answers, in 70% of the cases for in the best model, they had stigmatizing reasoning in the reasoning traces, and we got this evaluated through actual therapists. And so this is kind of the safety washing problem, right? Models will pass the outcome level benchmarks, but in this case, they might have some stigmatizing internal logic still present, and that won't be very obvious. So it could ace all the benchmarks, but then it could have problematic behavior in multi-turn conversations with people, or have long-term behaviors that might be not helpful for the individual that's trying to get assistance. Right. I think I've taken a lot of time, so I'll stop here and I'll end with a few learnings that I had through my research. Maybe this is helpful for all of you. So the first thing I wanted to point out was whenever it's viable, try to visualize whatever you're working on. Um, I did that a lot, especially in my early research, and it gave me a lot of ideas. It helped me wrap my head around problems and also to communicate what I'm working on with other people. Another thing that I found was selecting simple solutions often really works. So calling back to the simple incentives approach, it was beating the neural network approach without needing any learning. It was a fairly straightforward thing that we did, and it ended up being very strong. So if straightforward solutions work, you should lean towards those. And the third is build better evals. Not all benchmarks, not all common evaluations are applicable to the problems we are working on, especially in the responsible AI domain. There are a lot of edge cases, a lot of new problems that we are working on, and we often need to build evals specifically for the problems we are trying to tackle. And then finally, building on this, we should work with domain experts. Whenever possible, it's responsible AI work is often interdisciplinary. It's cutting across domains, and the domain experts have years of experience, years of expertise, and it's very useful to rely on them to get you insights that probably data driven approaches might not be able to give you. So, those were my few cents about responsible AI and specifically in the context of my own work. I'll stop now and take any questions. Yeah, thank you.
Thanks a lot, Ashwin, for that really great talk. We actually have,
Uh,
sorry, I think I was muted. I was saying thanks a lot, Ashwin, for that great talk. We have a question from Ramya, which I'm going to sort of rephrase. And I think Ramya's question is asking about um, the bias in the RLHF models
Mhm.
and the distinction between the bias being part of the data set that's being used to train the reward model and the bias that's part of the actual reward model itself.
Mhm.
So in practice, how do you think about detecting and correcting for reward model bias distinctly from data set that's being used to train the reward model bias? And is there a point in the RLHF pipeline where the intervention is most tractable?
Right. So that's actually a really good question, and we did kind of explore this. I'm trying to find if I have the slides for it. We did kind of try to see where the bias is coming from. So I don't think I have the exact slides, but I can verbally communicate about it. So we found that indeed the data set bias is what's causing this issue. Um, so we did some zero shot comparison. Oh yeah, there's one slide. So we compared the same models, the same architectures without training on the data set. And you can see that all their bias directions are not aligned. Like this is a complicated figure, but what you want to see is that, let's say this green bar, it's different for each model. It's in different locations, which is the preference over one a man versus woman prefix, right? But after reward model training, they all line up. So this was a very strong indicator that this bias is coming from the data. And then we also had a sort of data augmentation solution. So this is more um, a responsive solution, I would say, than a purely theoretical one. But then once we know this kind of issue exists, it's not that difficult to augment the data set with counter examples and have them all really learn that this is not something that we should derive a signal from. So that's how we ended up solving the problem.
Got it.
Hi, hi, Ashwin.
Hey,
Yeah.
Ramya here. Yeah. Uh, Ashwin, thanks for the very good talk to begin with. So, Markov decision process is also my research area. So, I was quite excited to be a part of this discussion.
yeah,
So, on the same lines, I just have a couple of questions that I would want to understand. So, the first one is, do you have any assumption on the arrival process of the agents in the context of the first problem statement that you discussed?
yeah, okay. I had the slide which I hid away because I didn't want people to be scared by the notation. But I think so. Generally, the arrival process is we don't explicitly model it as something. So for all the problems we discussed, the arrival
Mhm.
processes are from real world data, right? So we're not
Okay,
assuming that they're following some sort of distribution. The
okay.
the goal is to make the model as general as possible, and then obviously we can have specific instantiations if we have information about a particular domain. Is that kind of answering your question, or were you asking something else?
Yes. It's the same question. I just wanted to know, do you have any assumption that talks about the policy characteristics or something?
Okay, yeah. No,
Uh,
so we don't make that assumption.
Sure. Okay. And then the second question was, so you are trying to do the same resource allocation problem for LLM agents. Is that right? Or they're two separate problems?
They are two separate problems. So I think they are linked in the sense that it's more of a conceptual link rather than a theoretical link that
Okay.
agents would make decisions for us. So that's in the space of all bias and responsibility. I wanted to talk about both things because I had plenty of time to talk about them. I wanted to give like a brief flavor of all the different things I've done. But
Mhm.
they are two different problems. Yeah.
Okay. And maybe one, just one last question. So I was trying to understand the objective function of the, underlying optimization problem that you're trying to train on. So you
Mhm.
came up with a different metrics. So you were talking about bringing the utility up for each individual person who's driving the vehicle.
Yeah.
And you were also talking about the availability of having a ride for the individual who's trying to book,
Yeah.
and then fairness. So obviously fairness, I understand is that's the QF part. So what is the QU part in these two things, or it's a combination of both?
Yeah. Okay. So I'll use the slide again. So There are three competing forces here, and you're correct to point out that the objective is kind of not very clear. The first thing is that overall, the decision maker is trying to optimize for one thing, which is maximize the total payoff for everyone in the system. So, in the ride sharing example, they're trying to make sure the drivers get a lot of rides and passengers get served a lot. Right, so that's what the decision maker is trying to do. The QU is what the taxis do. So each taxi driver is kind of estimating, okay, if I get this passenger, I'm getting this much money out of them. Or in the long term, maybe I go to a busy area of the city and later on I have the chance to make more money, right? So that's what the QU part is doing. It's the long term estimate, is the reward to go, in a sense, if you're familiar with it. You said you're working with
Yeah.
MDPs. So yeah,
Mhm.
so QU is the reward to go, and then QF is what we're trying to modify the overall Q function to be to also account for fairness.
And on these also, there's no assumption on any convexity or linearity or any polynomial, nothing on
There
the
is
function.
some, so for the second approach that I talked about, which is the general incentives one, there are some assumptions for this one. I think there's monotonicity assumptions, but I think that's the big one. So there's monotonicity, and there is the convergence assumption of the utility functions. QU has to be convergent, correct? Those are the assumptions that we have.
Okay, thank you very much for answering my questions, and not having too many assumptions is a very good model. Thank
Yeah,
you.
thank you. Thank you for the questions.
Hey, Novanil, Jyotimaya here. Can you give me video access? Hey, Ashwin. Hi, how are you?
Hi, Jyotirmay. Nice to see you again. Thank you
Yeah,
for
after
inviting
so
me.
many years. Yes,
Yeah.
yes. Glad to meet you. And I'm sure Nav has introduced you to all of the audience. But thank you very much for accepting our invite and sparing time. Hi.
I-
Yeah. Yes. Okay.
yeah, of
So
course.
do you keep coming back to India?
Uh, I try to once a year. Yeah,
All right. All right. So next time when you are here, let us know. Maybe we'll invite you to the campus itself.
that would be great. Yeah, I do come to Bangalore. My brother is living there, so uh, it sounds like a plan.
So are you in touch with anyone back at the university now?
Um, I talked to a couple of professors, but mostly other alumni. Yeah.
Okay. All right. Yeah. Okay. Good to see you. Okay. Nolan, is there any other further questions?
I think I saw a raised hand.
Okay.
Arnab, did you have a hand raised? Okay.